Nice to meet you. Guten Tag, guten Abend, good evening, and etc. I will talk about machine learning model in Apache Ignite project. And of course, let's start without some welcoming slides. And please raise your hand who use Apache Ignite, for example, in production. Maybe somebody. OK, I see one person. Cool. I will talk some facts about myself. For last 6 years, I've been studying for source code for many distributed instruments like Apache Spark, like Apache Hive, Apache Ignite, and etc. and etc. Maybe you used TensorFlow, not Apache project like Harvard, like TensorFlow, and etc. All of them are open sourced. And last 2 years, I've spent a lot of time to build enough good ML module of the Apache Ignite. I will talk some words about what is Apache Ignite because not so many users are here. First of all, I will give you a very simple definition. It's kind of in-memory database. Yes, it has so many features, how to persist on the disk, how to support cache operation, etc. But now, for many use cases in production, it's a memory database. Maybe you could find some parallels with Cassandra or with React, but it fully supports ACID transactions. First of all, it has distributed SQL. These two features are so good, and 2 years, we started a special model in Apache Ignite ecosystem. It was ML module. First of all, it was linear algebra over the Apache Ignite. But now it's more than algebra. Now, raise your hands who at least trained the model maybe in pet project. Me. OK, so many ML guys here. But who used Spark ML for this, for example? Most of them. OK, cool. I will talk some information about traditional programming, about machine learning programmer, and the usual program that the programmer writes resembles a finite state machine, you know, and generally consists of a strict set of instructions. In the machine learning, we have the opposite situation. We need to generate computations, the model, and ML task shortly could be described as a search of the best set of parameters for unknown function f, which has known type. For example, it's a line, or it's a cubic line, or something else. It could be complicated. More strictly, we have the task of objects x. Y is a set of answers, and f is an unknown relation, finding objects and answers. And the goal is to approximate this unknown function by another function with known hyperparameters. For example, let's start from the simplest model, the linear regression. This is an example of linear regression. As I said, it was mentioned 2 talks ago in Hive Mode talk, which describes the linear dependency between input and output. And our goal to find the best set of W coefficient, right? And how to determine which line is the best. Here, the loss function will help us. MSE, loss function, this is a difference, sum of square deviations between predictions and true answers known before, for example, on the labeled data set. And we are trying to minimize the MSE result to find the best function. I know that all ML guys know this fact, but we need some introduction here, sorry. And a model can be represented not only via, for example, linear equation or something else, but also as a tree, for example. And this slide is shows a Titanic passenger data set survival prediction model as a binary tree. This is a very known image. And the next, we are trying to find a certain curve that divides the set of points into 2 classes. There are a lot of these curves, and we need to find a curve that separates these classes in the best way, according to the last function. We should remember this definition to the next slides. Imagine that we have a lot of data in the cluster. we will not talk that this is an Ignite cluster. In many cases, maybe it's Spark cluster, Kafka cluster, I don't know, Row, Kubernetes cluster, etc. And we are trying to find a way to predict on this data. Of course, if you load this data to Apache Ignite, for example, you can train on this data in memory, in the real time, etc. And Apache Ignite ML library supports not only distributed training, it supports distributed preprocessing, evaluation, parallel cross-validation for higher cluster resource utilization, and so many things. Let's start from the first point. You have a raw data, for example, in Apache Ignite or in Kafka. You can use special data streamer to load the data into Apache Ignite in memory tables. And the distributed pipeline starts from the data loading, first of all. After that, via preprocessing, we should prepare a set of vectors. Of course, many algorithms likes data with double values, not with strings, not with strange enums, not with Java objects, and etc. And the goal of preprocessing to prepare vectors. After that, then vector contained only doubles. We train the model on the vector data. After that, we need sometimes, not in 100% cases, we need to repeat our training process again and again, and we don't want to spend the time to prepare this code in Java every time. And here, it's very easy to use something like ParamGrid, cross-validation, pipeline, API, and etc. For example, like in Apache Spark. But Apache Spark is not the in-memory database. You should remember that. And at the end, the quality of the build model could be evaluated before deploying on the production. It's a very interesting point. We have a lot of different metrics how to estimate the model. And for binary classification tasks, for regression, for clustering sometimes, and etc. All these steps are distributed in Apache Ignite model. You should ask me, how? We have the same thing in Apache Spark. Yes, we have the same thing in Apache Spark. Apache Spark and scikit-learn are reference libraries for the Apache Ignite model. But I have one small problem. The Apache Spark has a stable, ML lib, has a stable core which has no, I don't know, ability to aggregate new pairs which located in many issues in the Apache Spark Jira. There are a lot of different PRs, and my goal in Apache Ignite ML to use this experience, of all these users, to involve them into new distributed library, which have a chance to merge all these algorithms to support all new features and etc. I'm not trying to, for example, for you say, please drop Apache Spark ML lib. No, this is for different use cases. Apache Spark ML lib is good for the real big data cases, and you have a lot of data. Then this data is managed by Hadoop cluster. But if you have medium data for in-memory cluster in Apache Ignite, you need prediction tool too. And this is a bad idea to move it into HDFS to train in Spark, in Apache Spark. But Apache Ignite has connection to Apache Spark 2, and you can load data from the Apache Spark data frame operations to train in memory mode. Also, like in Apache Spark, it uses internally distributed data structures. It's presented like a partition-based dataset. This is an abstraction layer which sits between machine learning algorithms and the storage, Apache Ignite caches. And it uses MapReduce-like approach to perform the computation. Of course, in distributed world, you couldn't avoid MapReduce, right? And for many tasks, you can find your custom approach to use MapReduce approach directly, not via, for example, data frame common approach in Spark, not via RDD API, and etc. But you can implement your own partition data structures for each algorithm. For example, linear regression and the SVM algorithms has the same partition structure, but for example, the decision tree has another. And you can find the best formats to prepare them. In Apache Ignite ML, we are trying to find the best way to present data for each algorithm. Yes, we have a common approach which can be used in your algorithm, but if you want to implement your own storage, you can as a contributor. Let's talk about ML algorithms. Of course, it has a lot of classification algorithms. It's classic library. You have logistic regression, SVM, KNN. I know that it's not distributed well, but you can try. And we implemented INN approximate neighbors. I'm sorry to repeat this. INN is approximate KNN. Decision trees, random forest, and random forest is not only one, the ensemble method for the ML library. Also, we support regression algorithms, and of course, if you like the very initial neural network architecture, of course, we support multi-layer perceptron, and it uses internally in logistic regression like one-layer perceptron there. And let's look on the next, I don't know, I name it like architecture diagram. Let's say. We use Ignite caches to extract the in-memory data to build a partition-based dataset. First of all, a partition-based dataset is special structure across the cluster, distributed across the cluster, but it's not the raw Ignite format. This is a special format for the machine learning. We don't want to reuse Ignite caches because they are was built for another cases, not for machine learning. But we use it like data source, and we minimize the shuffling between the nodes. Partitions are created near the data, located in the Apache Ignite. Okay, first of all, fill the cache. For example, we read Titanic passenger data set to predict who will survive, who not, and we build, first of all, Ignite caches. After that, we make labeled vectors, vector with label, from raw data in caches via, for example, dummy vectorizers. We have a lot of them, this is the limitation now of Apache Ignite. We have no full access to the data scheme in Apache Ignite, and this is the reason why we work with indices now. But I think that in next releases it will be fixed, and we will work fully with the meta information like the column names and etc. Yes, this is the issue. After that, we define the trainer, decision tree classification trainer with 5 as max deep of 3 and minimum impurity as 0. And after that, we feed this training algorithm to the Ignite instance. For example, Ignite session declared before this slide, data cache declared earlier, and vectorizer. We combine them together and feed on this data to get the model. And after that, we use evaluator to evaluate our results. Okay, it's Java, we use generics and so on. Preprocessors. Of course, the sun will die before we implement all preprocessing from scikit-learn. Now the Apache Spark is not the reference here because scikit-learn has much more here. And all preprocessing could be distributed well because in 90% cases, it has only one MapReduce step, sometimes 2, not n. The amount of preprocessor could be compared with Spark, except the NLP preprocessing. And of course, we have normalizing, vector to special normas, standard scaling, min-max scaling, max ABS scaling, and etc. and etc. And of course, we support on hard encoding because we need to prepare our double vectors. I think that maybe part of you who sitting there not familiar with this. Please imagine you have something like Java enum. I know that most of Apache developers are Java developers, but maybe not so all. And we need to present this enum like a binary vector. For example, with digit 1 or digit 0 on the special places. For example, we decided that the first column we will put 1 there, it correlated with the first ordinary item in the Java enum, etc., etc. let's combine together preprocessing, training, and evaluation. We could define the previous steps here, for example, imputing to fill missed values, min-max scalar to scale, normalization if you need normalization, and you could see that the second preprocessor uses the link to the imputing preprocessor, normalization preprocessor use min-max scalar preprocessor, and etc. The decision tree classification trainer use the last one, a normalization preprocessor. And of course, all calculations are lazy. In reality, where you call the feed, no calculation are running. But when you call the trainer feed, all calculations are started from the first preprocessor. Let's go deeper to the linear regression. Linear regression could be implemented via different approaches. There are a lot of them on the internet, archive work, and etc. But let's talk about a few algorithms which could be implemented in distributed manner easily. The first algorithm which was added historically to Apache Ignite was the linear regression via LSQR method. LSQR method, it reminds me the SVD. SVD, I mean singular value decomposition method. The core of this method is the bidiagonalization procedure, Golub, Kahan, Lanchos, I don't remember exactly how to pronounce that. And the pseudocode could be listed like this. And we need to understand how to move this code to the MapReduce operations. We could improve the equations on the slide. We could rewrite them for p parts, for example, at p index in each equation. And in the final, we need to MapReduce stages for each step to perform the calculation. And having selected p steps, we can transform the set of expression, like here. And it was the first algorithm which was implemented. Maybe not very simple, but it was very useful implementation, which you used in many libraries. Another interesting algorithm is stochastic gradient descent, which is used in, I don't know, in half of our algorithms, but not in all algorithms, as a core of calculations. For example, we have, you should remember this linear regression model, and we need to find W coefficient, right? And let's write yet one time MSE loss function. And what we could do here, we should minimize the MSE functional. We should get the first derivative of each target variable, right? And the vector of such derivatives named as gradient. And it indicates the direction of the maximum increment of the function at the point. Each point, for example. And we can change the W vector of our coefficients according to the value of gradient by special formulas and so on. Iteration by iteration, iteration by iteration. And this calculation could be distributed. The gradient operator is linear and could be calculated on data partition in parallel on different nodes, for example. I don't know, on different cores if you run it in parallel mode, not in distributed mode. This is a simple visualization how it works. There is no difference between distributed gradient and non-distributed gradient. It gives us the same result here. This code shows how to use SGD to update the linear model coefficients. This is not real production code, but this is like a schema. This is a placing code that wastes a lot of time, I don't know, 99% of time, and it should be distributed due to the easily distributed nature of the gradient calculation, as was mentioned on this slide. This is how we work in Apache Ignite ML model. We trying to find a paper, how to distribute it one or another algorithm. We find the place and code which could be separated for different nodes. We are trying to find the reference implementation. Sometimes the reference implementations in another distributed frameworks are not so good and has special limitations. But for the last 2 years, On the archive.org, we're printing a lot of new papers. There you can find new approaches to distribute, for example, SVM algorithm and so on. The new frameworks presented in C++, which could be I don't know, became a part of Apache Ignite ML or another library. I hope that some new solutions which were implemented in our library could be a reference for another libraries too. This is not the closed source world. And why do we spend a lot of time on SGD method? Because it's working horse for many our algorithms like logistic regression, simple neural networks, linear regression, SVM, and etc. And if you understand how to implement the SGD method, you could understand the sources, for example, of TensorFlow, PyTorch, in different neural network libraries. Sometimes it's difficult to evaluate how good this or that binary classification model. And the first idea is splitting of the initial data sets on test and train data set. Okay, we support this, it's very simple. But sometimes we could get on this operation the effect of the overfitting. And the next idea is k-fold cross-validation. And during this process, Ignite splits our data sets in k consecutive folds, and each fold is used once as a validation, while k-1 remaining folds form a training data set. And of course, we could run these calculations in parallel if you have enough resource cluster cores, for example, and etc. Because in reality, the training not spend all your resources, not all your memory, not all your CPUs, and etc. Also, of course, each ML developer likes ML pipelines, and Spark has a very good support of pipeline APIs. And I'm trying to repeat this for newcomers in Apache Ignite ML. It will be very easy to understand what's happened here on the slide. But we implemented more different parameter search strategies, not, I'm sorry, stupid grid search, but a random search. And for example, this summer I added evolution optimization strategy. Maybe you know, for discrete optimization task, there are a lot of different heuristics how to find the best solution on the set of discrete values, for example. And this is one of them. Or you could use another approach here. You could add new approaches to our library too, if you will be a contributor or committer in our project. And if you don't know what is genetic algorithm, maybe you remember something from the university courses and etc. You saw on the set of hyperparameters, like on the genes of the I don't know, person in the population, and you need to mutate them, cross over them, reproduce them to find the best solution. Also, in our library, they have not only genetic algorithm to tune hyperparameters. We have support of distributed genetic algorithms too. It was a very large donation. It was in the early times of our model, and it works well. There are a lot of different examples. If you need distributed genetic algorithms, you can go and use these algorithms too. After that, we could finish all these pipelines with cross-validation and hyperparameter tuning. We need to declare the instance of cross-validation and run the tune hyperparameters function to get to, first of all, to mix all previous operators together and find the, for example, for the decision training algorithm, the best max deep and mean purity decrease hyperparameters, which were presented here like a set of different values. That's not all. Of course, we have ensembles. This is a part of topic today, and maybe someone of you trying to join this talk to hear something about distributed ensembles. Yes, we have full-featured distributed ensembles. I mean, staking, bagging, and boosting. Not limited edition like in Apache Spark. Sorry, Apache Spark, but this is the reason why it's located in Apache Ignite. Ensemble learning builds a set of classifiers in order to enhance the accuracy of a single classifier. For example, the random forest. You know, random forest you should train a lot of different trees on subset of data and merge the results of voting, for example, like averaging or calculations the max value of votes. For example, you vote for the first class or for the second class, and 100 of trees trying to vote. But of course, you can use your own custom voters, vote procedures, and etc. Let's start on the bagging. This is also called like bootstrap aggregation. This is a special machine learning algorithm which has a common schema for mentioned earlier random forest. Random forest is kind of bagging here, for example, we're starting from the splitting the initial data sets on the train and test set, and trace set could be splitted on the special bags, and you can train different models on these bags and join the results. For example, via voting, or for example, for regression tags, via special mean procedure, then you're trying to find the mean value of all predicted results. Also, we have a boosting, and in my opinion, boosting is not a good candidate for distributing, but it's good candidate for sequential execution, of course, but all training could be distributed. For example, you have a lot of data and your subset of data is too much and should be located in cluster 2. This is the reason to use our boosting, not another one-thread boosting from cool Python libraries. Also, we have a staking. Staking involves training a learning algorithm to combine the prediction of first step algorithm to predict the inputs for the second level algorithm. For example, we have partition-based dataset, train free decision tree model, and train the logistic regression on result of prediction of this model. This is a very popular technique on Kaggle, you know, and then combiner algorithm is training to make a final prediction, used all of them. It could be very easily used in Apache Ignite ML, for example, via next code to get the result. You train here 2 decision tree classification models and combine them via special staked vector dataset trainer. There you add easily your required trainers defined above and feed on the data to get the staked model. Also, we support kind of online learning. Maybe it's not the final decision for our library, but we support online learning for all of the algorithms because each developer who starting to add new algorithm to our library should implement the update model method to training partially. It reminds me the partial training in scikit-learn, but as we know, scikit-learn has no distributed version to train partially in distributed environment. Sorry. Online machine learning is the method of machine learning to add new information to your model based on the new portion of data, for example. Let's imagine you have Apache Spark, which has connector to Apache Ignite. You build the pipeline, you prepare the data, you reduce the data, and load to Apache Ignite. And you need to update the trained model via data pieces from Kafka. You could use Apache Spark, but it has a very, very limited support of online learning for 3 or 5 models, I don't remember exactly, via very complex formulas, etc. But here in Apache Ignite, you could easily use update method to update your previous model via a new portion of data, loaded via data streamer. I'm not going to add the code of loading, but you could see how to use update method here. You have a logistic regression trainer. The all hyperparameters with it on the first portion of data, on the data cache 1, and the model 2 could be built via model 1 updated with portion data located in data cache 2. It works for all of our algorithm. I agree. This is a very interesting field. I mean that now on archive.org, of course, there are a lot of papers how to do these models which should be updated online in real time. There are many different heuristic approaches, and you could go to our community and implement what you want for new algorithms and maybe something rewrite for the for old algorithms too. Also, in the end, we will finish our talk. I want to say some words about TensorFlow integration. Of course, we have two ways in our community to build our own neural network framework above Apache Ignite or use the existing. We started from the multilayer Perceptron. We played with reinforcement learning architectures in PRs and etc. But we understand the power of community is limited, and we should collaborate with existing cool solution like TensorFlow. I know that many data scientists use PyTorch too, and I hope that somebody who will go to our community could help us with this integration. But I'm not a PyTorch user. I'm enough good with TensorFlow. I could understand the source code and etc. And it was the reason why 3 of us collaborated with TensorFlow, and we created a special bridge for that. We made a few commits to Apache Ignite to prepare all infrastructure for integration, to TensorFlow for bridge. It's located in special TensorFlow IO package or something else. It was in one place in TensorFlow 1, and it's in another repository in TensorFlow 2 because of evolution of TensorFlow. And for TensorFlow, we supported saving to our in-memory file system, supported loading from Ignite Dataset data to the TensorFlow to train on them internally in TensorFlow, and we support the distributed backend, like a Haravot, but historically our distributed backend was earlier because we don't know about Haravot and implemented this, and guys in TensorFlow doesn't know about that 2 years ago. We provide Apache Ignite integration like distributed backend. You could use this backend like for distributed calculation of gradients in TensorFlow. For example, here this is example of loading data from the Ignite dataset, for example, from SQL public kitten cache to iterate on them, to print out the data. This is another example in Python, how to distribute your calculations via TensorFlow device, how to run the job, and etc. All examples are actual for the TensorFlow 1. I think that in next few months we will support TensorFlow 2. Again and again, I will say, if you want to support TensorFlow 2, you could go to our community and could help, because you know we have not so many hands for that. But we have so many opportunities. And it works like how you create separate TensorFlow instances together with Apache Ignite nodes, and it could easily communicate with TensorFlow boards and so on. Also, sorry, in the end, I should say about some integration points, because for this talk, for me, this is a purpose to invite you to our community, to invite you to build the Apache Ignite ML, and I want to talk about few opportunities, because the first opportunity for newcomer is integration. You know one tool, you could integrate it with our tool, and this is a point of collaboration. And we have different support for model inference. This is that means that we could get the model, train it in another system, load to us, and predict on our data. We have special infrastructure for distributed inference, and for example, you could load data from scikit-learn via PMML, but we have very limited support for PMML format, but of course we could extend it in future. We have full support for XGBoost models. We have support for all Spark models which has the neighbor in our library. We have full support of MLeap, this special tool in many times for Spark-only model to load and predict on trained Spark pipelines, which were trained in Spark cluster, for example. We have 2 points to integrate with Spark. We directly parse the Spark binary format, for example, Parquet files, and so on. And another approach is to use MLeap runtime. We don't know what will win in Spark community and trying to support all of them. And you don't believe, 2 days before this summit, someone from H2O community prepared the pull request how to parse H2O model to Inference in Apache Ignite. We didn't merge it yet, but I think that in the next release it will be merged, and we will have more inference points. For example, MLeap usage looks like that. We run MLeap context. We use special Ignite distributed model builder to build the model from the file system. Of course, in many cases, we should parse the file with special structure here. And this is a work for integration. This is not very difficult work, but very meaningful. If we have a lot of different integration points, we could make our tool stronger, of course. And we could make predictions on our model like on model trained in Ignite. For example, the architecture diagram looks like that for Spark ML model parser. You have Apache Spark, for example. You trained the model there. You use very usual method on a Apache Spark model write, override, save your model to the directory or to the file, to the Parquet file, of course, or to the directory of Parquet files. And we could parse, for example, this kind of model. This is gradient boosted trees, if I remember exactly. And we could load, for example, we could load new data, or we could upload, I don't know, new piece of information. We could load this model via Spark model parser parse method. There we have a special Java enum for all supported models. You could add new models there if you find them, and predict on this data too. It works. It could be your application. This is a motivation architecture diagram. If you have a lot of different points where you need to load the data to one storage, and you have not petabytes but terabytes of data, you could load the model from Apache Spark via Spark model parser. You could load new piece of data from Kafka or Flink via data streamers to Apache Ignite. You could update the Spark model via partially trained models from piece of data from Kafka and Flink and merge them together, combine them together in one large model, which will be stored in our internal model storage. Yeah, how to contribute? How to contribute? I hope that all these slides wasn't so hard. I think that mathematical formulas, this is the reason why you have dealt with machine learning and etc. And if you're interested in, I don't know, in different challenges with distributed nature, with machine learning, with integrations, and etc., you could join our community. We have 200 contributors. 50 maybe committers and 30 PMC members. We have blog, we have Ignite documentation, separately ML documentation. Contribution to the documentation are welcoming too, like in other Apache Ignite communities too. And I want to publish some things for Ignite 3.0. This is a very, very long roadmap for us. We want to have more deals with NLP, natural language processing, more integration with TensorFlow. We want to work close with TensorFlow, with PyTorch, with H2O, add more clustering algorithms. We have not enough clustering algorithms now, only KMeans and EM algorithm. And we want to add very basic statistical package. Now we missed this one because maybe we have no cool mathematicians or statisticians in our community. And if you're cool and let's join us. And of course, we have a lot of tasks for beginners. For example, last year I've mentored 2 guys who takes the task with label for newbies, and we spend a lot of time on GitHub for reviewing on dev list to discuss new proposals, etc. And now both of them are committers, and I think that one newcomer will be committer too next year, I hope, because they did a lot of tickets. If you're interested in this project or this opportunity, follow me, join the Twitter, go to the GitHub, and join to the Apache Ignite community. Of course, we have not only ML tasks. If you're interested in distributed SQL, distributed caches, different operations, cool Java multi-threading world and approaches, you could join too. This is really, really hard job, like we like. We all together. Thank you. If we have time for questions, have we time? Do we have a time?
Yes, we have.
Maybe somebody is ready to get the ticket. I don't know. Okay, I will be here after this session. I think 10 minutes here, and I'm sorry, on the downstairs near the tea, and we could drink some tea and discuss distributed ML if you're interested. Okay, thank you.